me do this. Welcome to class, folks. Alternating series and a review on everything. And something I like to call the close enough tests. Because direct comparison, little and limit comparison, it's about creating something that is close enough. So let's think about these. When I say close enough, it's all about getting a function like direct and limit is ignore the y. It's about getting it down to something that's close enough. And getting down to something that's close enough to, let's say, a p series in these cases, 1 over n to the p power. If you remember, as a p series, 1 over n to the p power, we want to like reduce it down to this. And if you remember in this case, when our p is greater than 1, we converge. And when you diverge in other cases, else you diverge. So that's the p series. Now, when I say get it close enough, I want you to get rid of the extra numbers. Extra numbers. Get rid of terms that don't matter. What matters is the highest degree term, right? It's like when we did the limits going to infinity of like rational functions with polynomials, we only cared about the highest degree term. So extras are terms that don't matter. Why don't they matter? Because as you go to infinity, and I had like n to the 5th power and n to the 4th power. The 5th power, as you go to infinity, you are going to be significantly different. Like if n was just 1, these two numbers are the same. But if n is 2, okay, you start seeing a little gap. As you go to infinity, that extra n in the n to the 5th will blow away n to the 4th. Even if you put like a big coefficient in front of 4, it won't matter. So we only care about the highest degree term. So let's take each of these and write the close enough right here. So I'm going to show you what I mean. So let's take this number 4. What would be close enough to number 4? So I'm going to copy it right here. So close enough. So it would be, let's say this was my original 1 over 3n squared minus 4. When I say close enough, I mean, let's get rid of the numbers. This minus 4, it doesn't matter. This coefficient 3, dump it. So 1 over 3n squared minus 4 is close enough to 1 over n squared. That's what I mean by close enough. Get it to like a p series of close enough. All right? Let's say I did number 2 over here. Okay. What did we get rid of? We get rid of this minus 4 thing. So I'm close enough to 1 over n. N to the 1 power if you care. Now, let's try this number 8 right here. Okay. If I had this series, I'm going to write it out on the side right here, n squared plus 4. Okay, we get rid of the things that don't matter. So I'm going to get rid of this plus 4. All right, so, and then this n over n squared. Now, when you're down to one term, just cancel out one of the n's. So I'm going to cancel out one n, and with one n on the bottom right here. So it's close enough to 1 over n. Get that? So originally it was n over n squared, close enough to, but cancel out one of the n's. It's close enough to 1 over n. So if you maybe you kind of see that eyeball right here, cancel out one of the n's. I don't mind the plus 4. It doesn't matter because I'm going to infinity. If you had infinity John Smith subs and you added 4 to that, who cares? You already have infinity of them. The 4 is not going to matter. Even for John Smith. Let's take some other ones in here. Let's follow that same logic. Let's go to 10 right here. I know I'm jumping around. What doesn't matter in this case? So what doesn't matter? I'm just going to cross it off right here. These terms don't matter. Those are too small for the 2n squared. And this n and minus 4, that doesn't matter. So I'm just left with like 2s and 3s. The coefficients, get them out of here. They're gone. So I'm left with n squared over n to the 5th. And they might be like, wait a minute. I want to get it just like, I can cancel out 2 of those n's on top and 2 of the n's on bottom. So I'm left with 1, and then it's n to the 3rd. That's how many are left on bottom. So it's close enough to 1 over n cubed. Kind of seeing this close enough pattern. Let's go to 6. 6 is the same way. I'm going to cancel out that stuff right there. I'm going to cancel out, and then I'm just this 4. Who cares? And they have n over n cubed. Cancel out that n. I'm just left with 1. This is down to 2, so it's close enough. 1 over n squared. Now, I saved 5 for the last one because it's a square root, and you're like, well, what do I do to that? Right? Okay, you cancel out. First, you're like, yeah, this 7, gone. But then you have that square root over just an n. Now remember, that's the same thing as n to the 1/2 power over like n to the 1 power. So I can cancel out a half of an n on the top and bottom. You cancel out a half of an n, and you're just left with a half of an n on the bottom. So it's actually close enough to 1 over n to the 1/2 power. I'm going to write it in that form instead of the square root of n, so it matches my p series. You see how these are all close enough right now? Now, the idea with close enough, when we got these like polynomial fractions, is if we eliminate this garbage, just compare it to a p series and you'll be fine. If we know we converge when p is greater than 1, which ones are we going to converge at? We're going to converge right here. Are we going to converge right here? No. We're going to diverge because that p equals 1. That's like n to the 1 power. Same thing here. That's going to diverge. This one's going to divert. Oh, no, converge. 3. This one will converge. My voice will crack too. This one's 1/2. That's less than 1. We're going to diverge. So the idea with comparisons, we say, what is it close enough to? When you get some weird stuff all over the place with numbers and it's mixed terms, and it doesn't follow these simple piece series, or it's not a simple geometric series, I can say it's close enough to this. I'm going to treat it like that piece series. You're trying to get it down to like looking like a piece series, maybe. All right, on. All right, let's try some other ones. Now, so it's about getting close enough too. But like, what if it's not just polynomials on top and bottom? What if I mix types? I'm like ln of n over n plus 2. Stuff like that. Well, how do I get it close enough to something? And this is where direct comparison comes in. So if we're mixing up types, and the types I have are like factorials, exponentials, this is like the polynomials, this is logs, or just numbers. When you're mixing these types, remove the ones that matter the least. I'm going to say it this way. As you're looking at this, just have those cancel out. And what matters the most? It's in this order. Factorials. Why do they matter the most? Because as n goes to infinity, you think, oh, these would all go to infinity, right? But ln of n goes to infinity really slowly. It goes to n slower than polynomials. And exponentials, they'll go to infinity faster than polynomials. But the fastest of all is factorials, because factorials, you're always multiplying by a higher number, so it's just going to go to the moon, even more than the rest. So factorials is the most powerful. Then your exponents, then your polynomials, then your logs, and then constants. There's no factorials here. That's more coming for like ratio test stuff later on. But let's take 6. I have ln of n over n plus 2. Okay, normally you could just cancel out. Okay, you probably know. So I'm going to write that ln of n over n plus 2. You know, that plus 2, get it out of here. We're done. But ln of n over n, what do I do? Well, as you go to infinity, ln of n is just not going to matter compared to n. So you know what? That ln of n, that's gone. This guy is close enough to this guy. But guess what? Now, there's the whole thing with the direct comparison of what's... Okay, we can talk the technical rules, whatever. We're fine with this. 1 over n. Now let's take 4. Oh, okay. It's not a polynomial anymore. Who cares? This exponent thing. Okay, let's cancel out that 1. That doesn't matter. Now, this is like 1 over 5 to the n. And you're like, well, how did this? Well, let's treat this as 1 over n to 5 over 5 over n. You could actually rewrite this 1 over 5 to the n power. Well, what do I look like? I look like a geometric series here. This is not a polynomial. Sometimes it's not all just p series. I did a bunch of those. It might not be. 1 over 5 to n. This is going to be a geometric series test. This is going to be a geometric series. Remember from last time? And since my r equals 1/5, it's between -1 and 1, we are going to converge here. In this case, this is a p series from above. That's n to the 1. This one is going to diverge by p series, if you have to write that. Since this one diverges by p series, this one's going to diverge by whatever, direct comparison, limit comparison, whatever you want to compare it to, by the comparison test. Since this one's going to converge by geo, the original one will also converge by, you can call it direct comparison. I don't care. Comparison test. It doesn't matter for now. What I'm telling you here, this is going to work most of the time. This is going to work as much as it matters. It's shortcuts that are close enough to the real definition that I think for now, we're going to go with. All right? So remember, what is close enough? Now, so what if you took a problem like this? You're like, oh, it's a bunch of garbage all over the place. I want to make it close enough to something. Well, just like we did last time. I want to cancel out things that don't matter. You know what doesn't matter? This in pink. This +2, gone. These coefficients, gone. I'm left with n over the square root of n to the 4th. Might be like, well, n to the 4th, it's a square root. But remember, we're square rooting this n to the 4th. And when you square root polynomial, it's just half the exponent. So I can rewrite that as n over n squared. Which you can cancel out one of those n's, and it's close enough to 1 over n, the 1 power, or n. And we know this diverges by the p series. Since this one diverges, our original would diverge because it's close enough to this 4n over square root of 5n. So that's how that stuff works. Think of it as it's close enough to that p series. You're just trying to do the problems. So what if you had this? You got these -1 dealies in here. We haven't dealt with these. Well, it's the final form of our test that we're going to do this week. Alternating series. When we have this -1, it makes a series alternate. So for example, in this case right here, n was going from 1 to infinity. This series would actually expand out. If you started with 1, it'd be like -1 over 1 plus 1 over 2 minus 1 over 3 plus 1 over 4 minus 1 over 5, etc. Moving on from that. So that's what happens with that series. You're adding and subtracting. You're alternating. So how do we know if these converge or diverge? Now here's the formal definition. A sub n is greater than 0. Alternating series looks like this, where a sub blah blah blah, or it's n plus 1. Gross. And then it says, oh, this. So here's your rules that matter in red. You're an alternating series. If you have that -1 thingy, I'm even going to say thingy. So you got like -1 to the n power. Maybe it's -1 to the n plus 1 power. What's the difference? That just means the first term, if it starts with a plus or minus, it's the same idea. You got that -1 in there, the power. That's the first thing. Oh, the pattern has to get smaller. That means the rest of this. Like, so for example, the pattern in this case would be like 1 over n, because it's basically -1 to the n times 1 over n. Is it going to get smaller? And is that limit of that pattern? Basically, this one doesn't matter too much. Is the limit going to be 0 of that pattern? If this limit goes to 0, and we have that -1 theory, thingy, we're going to converge. So here's the for example. What if I had this series 1 over n equals 1 to infinity? We know this one is going to diverge by the p series. Right? We've done that before because p is equal to 1, right? Okay, cool. That doesn't work, right? But what if we had This one. I put the negative 1 to the n over n. Well, see, for this series right here, we have the negative 1 thingy. And then we're going to look at that pattern. What's the limit as n goes to infinity of 1 over n? 1 over infinity, which is 0. Since we are alternating, and since this 1 over n gets smaller, because it's going to go down to 1 over infinity, and the limit goes to 0, we're going to say this one converges by the alternating series test. We can actually say by AST, that's fine. I'm going to abbreviate it. So that negative 1 thing, if this, I was just going 1 over 1 plus 1 over 2 plus 1 over 3, 1 over 4, 1 over 5, that would not converge. But by alternating it, it does converge. These are the 3 steps that explain this. I mean, this says that this, if you want to see what this says, a to n plus 1 is less than a to the n for all n after a certain n. Basically, at a certain point. So technically, you could have a series that doesn't get smaller, but like it's getting bigger. But then when it goes to infinity, it gets smaller. Kind of like maybe does like this. Goes like, back down. So that could be okay. And the limit has to go to 0. Typically, I hate the 3 rules here. The pattern has to get smaller. The formula or whatever. I'm called the pattern. I don't know what the technical term is right now. But typically when you go to 0, don't they always get smaller? I guess the only case where it wouldn't get smaller is like if it was below the x-axis and getting bigger. So you really don't even need you almost don't need to test for this one. You just have to test for this one. What's the limit going to infinity? You're probably going to be fine. If it goes to 0 and it has the negative 1 thingy, it will converge. All right. Yeah, go ahead. Yeah. Let's look at some examples. Okay. I already did this. I'm gonna change that to 1 over n squared. Let's take this one. Oh, does it have the negative 1 dealie? Yes. What's the pattern? I'm going to say it's 1 over n squared. 1 over n squared. Now, technically, is this getting smaller? If you want to check it out, just start writing a few of them. 1 over 1. Be 1 over 2 squared, so 4. 1 over 9. 1 over 16. Yeah, it gets smaller. It's getting smaller, definitely. Now, what's the limit as n goes to infinity of 1 over n squared? 1 over infinity squared, which is 0. Yes, yes, yes. Guess what? We converge by alternating series test. On the AP test, you can abbreviate AST if they ask that question. I don't know if they do on free response, but you'd be fine with that. You can use on the AP test like common abbreviations that like a calculus teacher would know. Those are legal. Now let's check another example. You say, oh, everything converges. Take this one. Oh, do I have the negative 1 dealie? Yes. Is the function getting smaller? So here's the thing. If I plug this in, it'd be 1 would be 1 plus 1, 2 over 1. Next would be 3 over 2. Would be 4 over 3. And 5 over 4. Is this getting smaller? Yeah, because it's like 2, 1.5, 1.3, 3, 1.2. It is getting smaller. But let's check the limit as n goes to infinity. N plus 1 over n. Remember your L'Hopital's rule and stuff. That would be infinity over infinity, right? Then I got to rewrite that, derive the top and derive the bottom. It's actually limit as n goes to infinity of 1 over 1. Derive top, derive bottom, which is going to be 1. Does not equal to 0, so we're going to diverge. I'm so sorry. I went way too fast. Okay, so if that was too fast for you, people watching, hit that left button a little bit. Take that playback speed down to like zero point 0.5. All right, we stopped the video here. Bye.